low-level Java optimization. Without further ado, this.
Okay, so today I'm looking at a particular aspect of low-level Java optimization. And this is to do with what happens to a CPU after the application's warmed up, the code's getting nice and warm. What happens when the CPU cools down again? And in particular, what happens if it hasn't run a piece of code or used a piece of data for a period of time, and the code actually runs slower after warming up. And how can we see how much slower it gets, and what can we do about it in terms of trying to change the code? So, my name's Lawrey. As mentioned earlier, I did most answers in the world for Java and JVM on Stack Overflow. I'm a Java champion. My blog has had over 4 million views, and last year, open source software from Protocol Software was downloaded over 17 million times. So it's fairly widely used, particularly in banks. So we focus very much on microsecond latency services, so they're counted in single to double-digit microseconds. And a key element is persistent shared memory, where you've got a recording of every message in and out of each microservice. Sort of products we have, like here we have a core of event-driven microservices. Chronic Queue is one of the most widely used products that's open source. We use support data grids, and on the other side we also have now a distributed ledger technology for building microservices, but Byzantine fault-tolerant microservices, so that up to a third of the nodes running the service can be actively trying to defraud it, and it will still run correctly. But coming back to low latency, what is the sort of profile we're looking for? So this is a benchmark done which it shows new order single passing through the system and coming back with an execution report. So this is full round trip. So Quick Fix, for example, is a standard product, but as you can see, its latency profile goes up as you look at your worst, say 1 in 100, which is the 99th percentile, or 1 in 1,000, which is your 3 nines. So that's not necessarily a problem. This is acceptable for a large range of use cases. But if you want consistent latency, then you're looking at a different product, possibly a commercial product like ours. So what are some of the techniques that we use for developing that kind of code? Because this is running on the same machine doing more or less the same work. So this is an example of a use case we developed last year for a client, where they had an order management system, and they were able to achieve wire-to-wire, this is using the fixed protocol, below 20 microseconds, 99.9% of the time. Now this is in pure Java, without using any lower level languages. So it is possible to do reasonably consistent, low level, low latency applications with a real business application. So this is also recording. The queues here are recording everything in and out. So Q is, like I mentioned, it's one of our most widely used products, partly because it's open source. So it's one you can download and use. We've recently added a C++ version, which, as you can see, is faster. However, largely we're looking to support just multiple languages. So this year we're looking at supporting C++ more, which also gives us an increased interest in how to get the best low latency performance out of our applications. So what are some of the basic things that we do on any trading system to improve the consistency of the performance? So one of the things we do is we isolate the CPUs of all the critical threads that we want running. Now this is already implying that we're working on a bare metal machine, because isolating CPUs on a virtual machine it doesn't really achieve the desired effect. So what this does is we go and say, look, the simplest strategy is to isolate an entire socket. So say you've got a dual socket server, you isolate the entire second socket, so nothing running on that socket is anything but a critical thread. And that means that your L3 cache, which is shared across all the CPUs, isn't being polluted by non-critical threads. And keeping data in cache is a key way to ensure that you get consistent performance. So this is a Linux command, which allows you to isolate boot time command, which allows you to isolate particular CPUs, and then you bind individual threads to those CPUs. So we have a library called Thread Affinity that's open source, and that allows you to, in a number of different ways, assign threads to particular CPUs. Another thing we do is we suggest turning off the specter patch. So unless you know what specter does, allows you using speculative execution allows you to access memory you shouldn't, which is clearly a security problem. However, the prevention of this has a significant performance impact. So on a typical application, this can be between 15 and 30% slower. But if you've got a significant amount of traffic going between threads, it can be up to 4 times slower. So if you've got a reasonably secure system, you're not running untrusted code, it may be an option to turn off the specter patch to get a performance improvement. Similar to that is a meltdown patch. So what the meltdown patch is being able to see areas of the kernel you shouldn't be able to see. The way this is done is to maintain 2 views of the memory, one which has got more of the kernel, one which has got less for when the user code is running. And switching backwards and forwards has a non-trivial overhead, somewhere between 7 and 15% overhead, depending on your use case. So this particularly hurts when you do system calls, because it has to switch between these 2. However, it is a lot simpler if you don't need to have this patch enabled. And this is why some of these weaknesses are here, because they were chasing performance gains. But then, obviously, if you've got a system that's running untrusted code, that's not acceptable. So then the solution in a lot of trading systems is don't run untrusted code. You should only be running code that was very carefully put onto that server after many series of testing. Another thing we do is turn off C states. So C states allows your computer to save power by switching between different states of power consumption. So when it's in state 1, the CPU is fully turned on, all the caches are turned on, and it's running at highest voltage to run as fast as possible. However, depending on the processor, different state levels all the way down to level 6 use less and less power. The problem is that the processor runs slower and slower. It's not entirely straight translation, but different states have less power consumption, but the CPU runs slower. There's also an overhead in switching between these states, which causes a short delay in your application, which is measurable. So the simplest solution is to ensure that you stay in the C state of 1 all the time. This draws more power, but on the plus side, you'll get much more consistent performance. Now, even with all of this, even if you're staying in C state 1, what the OS and even the BIOS can do is adjust the frequency of each CPU. And all the cores on your socket can actually be running at different speeds. They're always some multiple of an underlying frequency, but they can actually be running at different speeds at different times, depending on usage. So it'll fluctuate the speed up and down. And the variation can be a factor of 3. And that variation can be quite significant, particularly when you have a very short request. So as you saw earlier, we're trying to deal with a request end to end, and that's going through multiple hops and multiple threads within 20 microseconds. So if you go slow for the first 20 microseconds or 50 microseconds of any request before it realizes, hey, I want to do something, let's go faster and push the frequency up, then that's already too late. You've already dealt with it. So your CPU can spend all of its time running at 1.2 gigahertz, despite what it's actually rated as, because it never gets to the point where it thinks it's busy enough that it warrants running at a higher frequency. So by default, a lot of systems run it in either a power save or conservative mode. And like I said, for a low latency system that doesn't have a particularly high throughput, you can be running at 1.2 gigahertz all the time in reality. So what you can do instead in this model is you can tell it that you want to set the governor to performance, and the minimum and maximum frequencies you set to the maximum, whatever that machine is capable of. Now, this doesn't strictly improve the performance, it improves the consistency. Because in reality, doing this is most likely going to disable turbo mode. So turbo mode can give you even higher frequencies again. However, by running at busy waiting and running at highest frequency all the time, you're going to heat up the CPU, and it's going to be less likely to ever go into turbo mode. So one of the things you sacrifice by doing this is you're probably not ever going to be in turbo mode. Okay, so even after you've set it, what you should see is now that the CPU frequency is what you set it to, 2.9 gigahertz. But the reality is you're only telling the OS what to do. The BIOS, in many cases, actually overrides the OS and says, I know better, so I'm going to control frequency instead. This has two downsides. If the BIOS is interacting with your application too much, it actually generates more interrupts and delays into your system, which the OS can't even see. So the OS there's no way to monitor it from the OS level that you're getting all these interrupts. They don't come up in any interrupt counters. But you will see jitter in your application. And so different BIOSes and different platforms will have a different sort of amount of noise depending on the settings. So in fact, going into your BIOS and switching off power management can actually reduce the amount of jitter, because it reduces the amount of interrupts on the CPU to monitor them and play around with their speeds and so on. Interestingly enough, just because you might set it to, say, 2.9, or I've got a desktop that supports quite a lot of high turbo mode. If I set it to 3.6, what I actually see is, because the BIOS interferes, it'll actually run sometimes at 4.2 or even 4.5. So just because it often sets it lower doesn't mean it won't even set it high. It just ignores the OS and then just does whatever it likes. You can actually see this by repping on CPU info. So you can see on this particular system, I've set the minimum and maximum to be 2.9 gigahertz. And as you can see, it hasn't taken a lot of notice of that command. You're running every CPU is running at all sorts of different speeds, although a lot of them are sitting at around 1.2 gigahertz, which is the minimum level in reality. So these are one of the things to watch out for, is if your BIOS is not set up right, it will just ignore your attempts to set it to the highest frequency all the time. So one of the tricks for encouraging a CPU to stay at high frequency all the time is to busy wait. When you're busy waiting, what will happen is that it will see that it's busy, and it will keep the CPU high. And that will ensure that it stays at the highest or close to the highest frequency all the time. So when it comes to being how to look at your CPU, when you've got multiple threads, in reality they're running concurrently. They're communicating via the L2 cache coherency bus. That's their mechanism for sending messages and data and synchronizing information between them. So one way of thinking of these is actually as a collection of individual processes communicating over a network. And an important detail is that the L1 and L2 caches are private. So that only means that, and so they've got about 1/4 of a megabyte each. They run completely concurrently. But as soon as they hit the L3 cache, which can be bigger, you're actually hitting a shared resource. So to get every one of those processes to run as fast as possible, you actually want your application for that process to run with only at about 1/4 of a megabyte, which is not a lot these days. Added to your difficulties is that Java doesn't really give you any control over this. So all you can really do is keep your code as short as possible, concise, and minimize your data sets if possible as well. And that can lead to a speed improvement, not only in your general throughput, but in particular in your higher percentiles when you're looking at the worst one 100, worst one in 1,000. So you can take an application like this. So this is what a more traditional application might look like. You might have some sort of enterprise bus in the middle, and you've got a number of different microservices communicating over an enterprise bus. This might be Ethernet, TCP, REST, whatever. But if you're mapping it at the low level, you're thinking about, well, how many cores do I have on a socket? So this socket has 4 cores across the top, 4 cores across the bottom. You can actually see where the L2 caches are, those big yellow bars. And the L3 cache sits in the middle. And using thread affinity, you can assign individual critical threads to individual cores. At this point, your high-speed bus is just the L2 cache coherency bus. And that's the fastest you'll get communication between any 2 threads. So now looking at so what can happen after your code is warmed up. So there is a problem with Java just warming up your code, which is getting code that hasn't been compiled to be compiled in the first place. Now, if you're working in C++, that's not really a problem because typically all your code is compiled up front unless there's some sort of generated code on the fly, which is relatively rare. But even after the code is compiled, without it being recompiled, which is another problem, your code can slow down again if it goes cold. So in this case, what's happening is that I've got 2 pieces of code written in different ways. So the blue line is writing out an identifier, where the identifier has a character followed by a long. So it's like N 20 billion. So things like an order ID or something like that. And then it parses it again. So it just renders it and then parses it. And that's all it does. The blue line uses standard Java, and the green line uses bytes library. So it goes on and off native memory. But for the most part, these are just 2 different code bases to do more or less the same thing. And both involve a certain amount of writing and reading, a certain number of branches that are difficult to optimize. So when the code is running hot, you can see you get very good latencies for this task and very consistent latencies. However, in the example above, the only difference I did between these is that I paused for a millisecond before running the code. So in the bottom case, the code busy waits for 100 milliseconds, and and you can see that there's a certain latency distribution, and this is worse than just running it flat out. But you can see that if you pause for a millisecond first, at then time how long that code takes to run, it's substantially slower. It's around 10 times slower if you've got conservative power management. And that's because what happens is that when the CPU is paused for a millisecond, it's enough time for the CPU to say, oh, I'm going to switch everything off now to save some power. It switches off all the caches, all the branch prediction caches, all the data caches. They all get switched off, and then they all have to start up again from scratch. So what you do before you run a piece of code can influence how fast that code takes to run. And in this example, it's about 10-to-1 ratio. And this is not an unusual case. There are more extreme cases where I've seen 40-to-1 slow. Now, so this is with the conservative or power state powering after a millisecond pause. Now let's reduce them significantly if you use the performance governor instead. But you still see a significant slowdown between running it busy waiting for 100 milliseconds and having it fall asleep. Now, there is a way of preventing this, which is actually reduces its usefulness of pausing for a millisecond, which is to fire off a thread that's running on another CPU that's just busy waiting. It's not doing anything at all other than keeping the CPU hot and then preventing it from switching off. And then you get this strange inversion where the CPU may have gone cold, so it's saved a bit of power. So sometimes, under the right conditions, if the CPU is not hot, it can come up at a higher speed than if it's too warm. But the reason why I'm showing you this is that used correctly, you can simulate with just a 1 millisecond pause what your code is like after it's come around under poor conditions. So when the caches aren't warm, the interrupts have disturbed the CPU in some way, the branch is not working for you, and you can simulate that with just a 1 millisecond pause before you do your actual test. Certainly on conservative, if you leave it in conservative power consumption, you can see a dramatic difference, and it really stands out how much slower your code can go. And what you can then do is, if you've got a way of reproducing this reliably, and you have to, as I pointed out, make sure nothing else is running on the system, or otherwise it will keep the CPU going, then you can optimize it for this case. Because you can now reproduce, you can try out your code in various combinations, loop it this way, loop it that way, change an if into a do while, or whatever it is that you want to change your code, and see how much that influences the code or not. So I've added to Chronicle Core a library to make it easier to do this. So it's just called Cooler Tester, and it has a whole lot of different coolers, pausing or busy waiting or yielding or doing a memory copy or switching between threads, so alternating between two CPUs backwards and forwards using affinity. So you jump backwards and forwards on every test. And then what it does, in this case, it repeats the tests 30 times, 30 blocks of 10 seconds. So it's about 5 minutes. So it alternates between these two 30 times, 10 seconds each, and then produces a summary, a distribution, which is what I used to produce those histograms just earlier. And so then you can see in a reproducible test, how much does it change my latency distribution, trying it one way or another. Now, I had hoped to come up with some really good rules of thumb that I could tell you about how you could just optimize all your code. However, for the most part, I found that this is really the thing you need to do, because there's a lot of trial and error in it. A lot of assumptions I made about what should make it go faster didn't make it go faster. And the most common thing I did was just delete code. I deleted a lot of optimizations. I thought it would make it go faster, and in reality it didn't. It often didn't make it worse either, but given the chance to make the code simpler, if there was no benefit, it makes it more maintainable for one thing, it makes the code shorter. So I found that removing a lot of optimizations was the most common change that I made that was useful. In some cases I did try combinations that made things worse. So for example, when it came to writing out the numbers, I tried printing it backwards, writing it backwards and then flipping them. And then also tried printing them forwards by working out what the top digit was and then writing it that way. And I found that that was significantly slower. It wasn't slower when everything was running hot, but it was significantly slower when it ran cold. So I actually reverted that and made it so that it now writes the number backwards and then reverses the number in order, in place. Some questions? Yes?
I was just wondering, in the last slide, you were talking about having a bit of code that enables you to plot a histogram of what's going on.
Yes.
But do you have any other metrics, like for example, the size of the application of L2 use or L1 use at that time, so you can, when you optimize, you've got like kind of a soft target. So you're like, okay, I'm definitely using too much L1, L2, or my branch code optimization isn't that great here. I can see that it's totally off and it's missing every time.
Well, see, what we're attempting to do here is we're skewing that quite a bit.
Yeah,
so if it's pausing for a millisecond, I'm trying to switch that off. So it should actually, you're really testing how good the harness is at getting a really bad hit rate.
Yeah, so you're getting the worst of.
Yes.
Yes. Okay.
And the reason for this is that it found that run busy waiting long enough, you actually get results as bad as sleeping for a millisecond, although it usually takes longer. And that threshold is around about 100 milliseconds. You start to see that happen. So if you busy wait for even 100 milliseconds, you can see results as bad as pausing for a millisecond in this case. So if you're doing less than 10 operations per second, so it could be less than 10 orders per second, for example, you could be running into this situation where your code is running slow because you're not pumping enough data, not pushing enough orders through your system to keep it awake. A common practice to avoid this is to just push dummy data through the system. But even without that, we're trying to optimize the code so that you will still get the best result possible even when your CPU is cold. Yes?
When it came to actually getting numbers for which ones, do you use JMH or is that not very enough?
So the problem with JMH is it tries to run things as fast as possible. So you only ever get the hot result, which is the best case. And what you often see in JMH is that you get comparable results, JMH versus JMH. But then when you put it in a real application where it's having to contend with the CPU, or you're trying to work out why my 99th percentile is so much higher than my typical, it's not such a good tool for that. So this is trying to solve for why is my 99th or my 3/9 much worse than my typical. You know, when things aren't quite so good, or there's been after an interrupt, or it's been after a context switch, or I've done some workload that's pushed things out of the cache, why is my performance not as good? It's trying to solve that kind of problem.
What was the 99.9%? Well, that number shot straight up, so I wasn't really sure what it ended up being.
Well, in the cold case, this is going into the 20 microseconds, which is quite a lot worse than at the same level consistently under 1. So one of the things that can cause it to shoot up that much is a TLB miss. TLB misses are really expensive, and you only have a fairly small TLB cache. A TLB miss is actually an OS call, and that's usually a minimum of about 2 microseconds, but 20 microseconds is not unusual. So if you're seeing sort of delays of 2 to 20 microseconds for no apparent reason, TLB misses is a potential culprit.
And that's after you've told the OS to not live on those calls. Or-
Yes, yeah, that's just the program
Yeah.
just
Just
having
the-
to hit
its
an
interaction
area of memory
with-
that hasn't been mapped in yet,
Okay.
or got mapped out of the cache. Yeah. But you do get things such as non-maskable interrupts, which you can't turn off from the OS, and then you've got interrupts from the BIOS, which is one of the reasons why tuning down the BIOS can help, which the OS can't even see, and it doesn't show up in any of the interrupt counters.
Have you ever wanted to upgrade a BIOS ever again?
Yeah, I have upgraded BIOS from time to time, but usually it doesn't seem to help much. You really need to, my experience, the best thing to do is get vendor support for people that supply the hardware, and they can tell you what is the best way to tune down a BIOS to turn on a lot of these features off.
So in a data center, would you recommend everybody just go to the high performance mode and
No. This is for particular use cases, right? So in most data centers, your power consumption is a key factor. This is more in the sort of a lot of systems in data centers. You're looking to run 30 to 70% busy, for example, and you've already got a fairly highly utilized system, and that's a normal workload. These sort of systems, your utilization, you probably want below 10%, possibly below 1% actually utilized. The reason you want such a low utilization is that at 1% utilization, 1 in 100 times, you actually have a queue of 2 hitting the system. So if they arrive randomly, so your requests arrive randomly. So at a 1% utilization, you've already doubled your 99th percentile. So it's quite bad already. 1% is already a bit high compared to what you might want to have. So in the example I gave before, you might have an order management system that can handle, say, 10,000 requests a second, but you might only get less than 10 a second in reality. So at that point, you're actually running at about 0.1% of your peak utilization, and that's to get consistent low latency on your messages. So you're actually running it. This is a very particular kind of system, really, in some ways. However, this kind of problem does show up. It solves the problem of why is it that my micro benchmark produces really good results when I put all these pieces of code together, the whole thing runs so much slower. And that's because they're starting to compete for resources. When this little piece of code had the full use of the CPU and all of the caches, it runs super fast. But when it's now having to compete with these other pieces, the drain on resources is too high. And now they're pushing just to run the whole section of code, they're pushing each other out of the cache to run these things. So now the branch prediction is not working. So using this, you can see, well, how badly can this code run individually? And when you add them up, you get something that's much more realistic to how it will run in a real application. And that's where it's more generally applicable.
Given you tweak the BIOS on hardware, if you write the same unit of code in C++, so can there be more performance gain?
Yes, so there are more performance gains, but you run into all the same problems because you're fighting against the power management and how the CPUs operate. So you actually run into at the end of the day, you're running more or less the same machine code. So you run into the same problem. So one of the things you can do in C++, which is better, is you can actually declare which branch is more likely to happen.
Mm-hmm.
And by doing that, when there's no branch prediction, you can ensure that the likely branch is always executed. Now, in Java, you can do that somewhat indirectly. By implication, assertions are always considered unlikely the way they're implemented, which is nice. If conditions are the very first branch of if condition, the way it seems to be implemented always seems to be likely because it's just done literally. As the code comes down, it just goes straight into the very first block. This is fine unless that is a condition that throws an exception. Right? So it's actually going to descend into the, when there's no branch prediction working, it's going to descend into that if condition and go and do some work, possibly even go work to do with the exception, creating an exception, and then have to back it all out when it realizes that no, it should not have gone into that branch.
Yeah.
So one of the things we've done is to change the code around so that the positive conditions are the likely branches, in as much cases as possible. Word of warning, if you, I've tried this, you put a likely branch, do nothing, right? Unlikely else, throw my exception. Compiler's smart enough to say, oh, actually your first block doesn't do anything, I'm going to throw it away, and it flips it back again for you. So it doesn't actually write the code literally as you wrote it. So you have to put some dummy statement in there to prevent it optimizing it away at compile time. That's another compile time optimization, of which there are very few in Java. But they're the sorts of things you can play with. Sometimes they make a big difference, sometimes they don't make any difference at all. And this is where some tool like this is actually a better way of trying this out than listening to any recommendation I can give you. I can only give you suggestions of what you can try. None of them I've found completely guaranteed, to be honest. A lot of them are around conditions that were expensive but rare, and it seems to be going into those. And if I flip it around, it solves some of the problems. Another one which seems to come up quite often is default methods. Default methods are usually optimized very well, but sometimes, and for often no apparent reason, they're not. And I've seen some significant performance improvements by just pulling the default method down to the implementation class, same code, and get a significant performance jump. But that doesn't happen consistently, right? This only happens in very rare cases where it's showing up as a problem. So I wouldn't do that as a general practice, but again, if you've got this kind of situation, you're trying to micro-tune something, and you're seeing there's a default method in the chain, something to try is, well, if I try pulling it down, does it help? And if it doesn't help, don't do it, because you're adding complexity for no gain. But if you can see that it really does make a difference in that use case, then it might help. So I've done that a few times in our code base, but again, it doesn't consistently help, but in some cases it's helped me much more than I thought it should. But that's why first creating a testing tool that you understand and you feel confident gives you meaningful results. This should be your starting point. And then from then, just try different combinations on the really critical pieces of code that you've identified. But however, my general recommendation is try and keep the code as simple as possible. And the reason for that is that the JVM has over a long period of time, has a big heuristics library of all different code paths that it recognizes. And they're all going to be common code constructs. So if you try and get clever, you will end up writing a piece of code it doesn't recognize, and it will be significantly slower. So every time you write something that's clever code, it's not only harder to maintain and understand, it's probably slower as well. Because the JVM doesn't recognize it, and it gets confused, and then doesn't optimize it as well. Which is rather sad, but true.
Do you recommend using lambda streams?
Again, lambda streams is one of these cases where you can get brilliant results in the sense that you get no performance degradation at all, but you get much cleaner code. However, there are rare cases where you can get much worse code. The biggest example I've seen is comparators used in sorting. Because comparators used in sorting are called n log n times, so they're called a lot. And if you chain them, that can cause a lot of megamorphic calls to lots of implementations. And that chaining can be very expensive, and because there's a lot of calls. So in the rare cases where I've seen that, you just create an anonymous implementation of a comparator that does the same thing, and you'll see a performance boost. That's the main example I've seen where you've got chained comparators used in sorting. It can make a difference not to use lambdas. But for the most part, the difference is in tens of percent. And for clarity over performance, clarity usually wins almost all the time.
What about parallel streams? Have you seen issues with the problem before?
Parallel streams, the best thing about parallel streams is how easy it is to remove. The reason I say that is that I've often spent a lot of time taking a piece of code which I thought should be faster if only you could make it parallel. And then by the time I've got it working, because it took me a long time to get it working and recode it and I put a lot of effort into it, don't always get enough time to test it properly. And even if I tested it properly and it worked, but it wasn't that much faster, my inclination is just to leave it, even though that's probably bad practice. I'm sure it's bad practice, right? Whereas if you've got a stream and you try it with parallel stream by changing one keyword and it doesn't help, you change it back. It's no effort. You don't leave lots of complicated parallel code all over your code base that never helped in the first place, or you never proved that it helped in the first place. Or it helped, but it just didn't work in combination with anything else. Because the reality is, once you've got enough parallelism that you're using all the cores on your machine, that's it, it's saturated. One of the first projects we did, we migrated from C# to Java. Because we were migrating from C#, there was a lot of lambdas in it. So we went live with a Java 8 project the end of 2014. So just about a month after it was released. It was quite great, going to production. It had 2,600 uses of streams. Because it had been migrated, there was a lot of uses of streams in there already. By some amount of trial and error, we tried different combinations as to which ones should be parallel streamed and which ones just didn't help. And we found that 3 was enough. 3 uses of parallel stream was enough to use all the CPUs in the box and get the best result. And the best thing about it was just how easy it was to switch backwards and forwards to try them out. And so many cases, in hindsight, I realized there's so many cases where I'd gone to the effort of parallelizing a code base and not done enough testing to really even prove that it was worth doing in the first place. Because a lot of the ones we tried, it wasn't worth it. We tried probably a few dozen and cut it down to just 3. So I think it's awesome, but it's very easy to overuse if you're not careful.
Preferred file system, X4, XFS?
We found that ext4 generally gets the best results for us.
With all the nmap usage and
Yes. We've had issues with ZFS ourselves, but again, your mileage may vary. But possibly because ext4 is simpler, I don't know. But it's just been our experience. That's true. It's largely the syncing of large numbers of pages. We can get larger causes of the whole system locking up with ZFS when we see the
sorry, that XFS.
yeah, I've only seen, I don't think we've done enough with
Did
ZFS.
do journal X4
No, this is Tony Jones.
and barrier 0 and
Yeah, just to optimize them as much as possible, to turn off as much as possible. Yes.
How much does raw VM change its game, if at all? Is it all better off again?
Possibly, because like I said, with the assumption that people treat the first branch as the likely path, it's entirely down to the compiler as to whether that's going to be true or whether it's smart enough to rearrange your code. To my experience, the Oracle one doesn't seem to be. But maybe Braille VM is smarter or will be smarter in the future. Maybe it isn't now, but it will be in the future. It would be good if Java had the same annotation for when you needed that control. it'd be good if the JVM just worked out that throwing an exception was an unlikely branch. Just you work that out statically, but he doesn't seem to. Yes.
Does hyperthreading have any sort of impact in terms of potentially thinking that core has exclusive resources with hyperthreading?
Yeah, so that's one of the tests that I did, and hyperthreading, enabling hyperthreading or not enabling hyperthreading had some inconclusive results. The biggest difference was if you're running two things on the same core, it definitely made it slower. However, if you enabled hyperthreading and just through isolation didn't use the second core, that seemed to produce very similar results to turning hyperthreading off. I know there is a technical difference between the two, but in terms of the benchmarks I was doing, there wasn't a large difference.
Can you tell the difference in the system between like a virtual hyperthreaded core and a real actual core? Can you tell the difference between it?
You certainly can in terms of performance, yes.
But can you choose that I want a real core as opposed to a hyperthreaded core to run on my end?
You can if you control the system, but once you're on the system, you can't tell the hyperthreaded core only run on a real one. Also, not all hyperthreaded systems are equal. I've seen enormous variations between different companies' implementations of virtual machines. In terms of our own software, we've seen variations of 30% slower to 10 times slower. Real versus virtual. And I don't have enough access to the systems to explain it, but just from our own benchmarks, run it on real, run it in hyperthread, you can see some startlingly different results. So not all hyperthreading implementations are equal in terms of how much slower they are. So 30% is probably acceptable, and 10 times probably isn't. Okay. Well, thank you very much for that.